Hey everyone, and welcome to this video. In this particular video we are going to talk about the spectroscopy. So our chromatography part is done. So if you haven't watched the video, you can go to our channel and watch those previous videos. I make very smaller and short videos for the concept purpose so that it is easier to remember. Okay, so in this particular video we are going to talk about the spectroscopy. So what does exactly the spectroscopy mean? So spectroscopy refers to the interaction of the matter with the energy. Okay, I know you must have seen this particular graph. So this particular graph actually show us the wavelength spectrum. Okay, so in what wavelength or in what frequency does the visible spectra exist? In what wavelength does the UV spectra exist? X-ray, gamma rays, infrared, microwave, and the radio waves. Okay, so like I said, the spectroscopy actually refers to the interaction of the matter with the energy. So whenever energy meaning light, so whenever the light will interact with the matter, or it can be the wave. Okay, so when the wave and the particle will actually interact with the matter, it will show some kind of interaction. Okay, so that interaction can be electronic transition, that can be vibrational, that can be rotational of rotation of the electrons, and it can be the nuclear transitions. Okay, so you must have read the very basic formula in the physics class, that is E equal to h nu. Okay, where h is the Planck constant, c is the speed of light, and the lambda is the wavelength. Okay, so nu directly corresponds to the c by lambda. Okay, so let so in this particular video we are going to stick with the UV and the visible spectrum. Okay, in the rest of the lectures we are going to cover the other part like infrared, the microwave, and the radio waves. Okay, so gamma rays, x-rays, and the long radio waves are not much of the importance for the gate purposes, gate or the jam, and even the CSIR net purposes, but here we are going to talk the important ones only. Okay, so first let's come into the very basic funda. Okay, so if we have a atoms, okay, so in the atom, so the electron revolve around the nucleus. Okay, so this particular black dot is showing the electron here. So whenever the energy in the form of light wave, in the form of wave or the particle, okay, will interact with this particular molecule, so with the, but not molecule, my bad. Okay, so whenever the light will interact with the electron, okay, it will give some energy. Okay, it will give some energy to this electron, and due to that energy it will jump from the lower orbital state to the higher orbital state. Okay, so if this is the ground state in which the electron is existing, so it will directly jump to the higher electronic state. Okay, so when it will emit the light, okay, or when it will emit that particular energy in the form of wave or the particle, okay, so it will come back to its original position, that is the ground state. Okay, so this particular phenomena, so where the electron is taking the energy from the surrounding or whatever source that we are giving, and it is going up to the higher state, that is called excitation. Okay, this is called excitation. And whenever it is emitting that absorbed light and it is coming back to the ground state, that is called emission. So excitation and the emission. Okay, so now let's come to the UV visible spectroscopy. Okay, so first of all, this kind of transition is called electronic transition. So like I said, we have like electronic transitions, vibration, rotation, nuclear transition. So for the UV spectroscopy, it has the electronic transition where electron is jumping from the ground state to the higher electronic states. Okay, so in the UV visible spectroscopy, the absorption of UV or visible light causes the transition of an electron from the ground orbital to the higher energy molecular orbital. Okay, so UV region in this UV visible spectroscopy ranges from 10 nanometer to 100 nanometers. Okay, and in this this UV region is subdivided into the three parts. Okay, the near UV region, where it is from 250 nanometer to 400 nanometer, far UV from 190 nanometer to 250 nanometer, and the vacuum UV, which is less than 190 nanometer. Okay, so wait, I'll change it to the pointer. Okay, so the vacuum is like less than 190 nanometer, although there is very less usage of this vacuum UV, but the near UV and far UV has much more practical application in the biological field. Okay, and you can see the visible region lies around from 400 nanometer to 780 nanometer. So this particular part is important for the gate BT and the gate axle part, because sometimes they directly ask from where does the near UV regions lie, and there will be option from 250 to 400, 190 to 250, 400 to 780, and the less than 90 nanometer. Okay, so just suppose these four options are given. Okay, so from this four option, so if they've asked the where is the near UV region, so you have to take the 250 to 400 nanometer. Okay, so this part is actually important. So let us come to the principle of this UV spectrophotometer. Okay, so for example, we have a light source. Okay, so here we are talking about the UV and the visible source. So it directly corresponds to the light meaning it is having the wave and the particle nature. I'm not going to the physics duality, but let us consider as a light only. Okay, so UV has the so for UV we use the deuterium or the D2 lamp, also called the hydrogen lamps. Okay, and for the visible region we can directly use tungsten. Okay, so these two are the light sources that are present in the UV visible source, and we have the monochromator. Okay, so what does monochromator do is it only allows specific wavelength of light to pass through this. Okay, so for example, if this UV lamp is on and I have given it the wavelength from starting from 190 to 780 nanometer. Okay, just suppose. Okay, so it will only allow the specific wavelength, and just suppose my specific wavelength for this particular experiment is 280 nanometer, the wavelength that is required for the absorbance of the protein. Okay, so it will only allow the 280 nanometer light to pass through, and not the others. Okay, and we have the solution. So this particular solution will be containing our protein. It can contain other materials which we want to like actually check. Okay, and we'll have a detector, and then we'll have a recording. Okay, so in this particular experiment what is happening is, so from the source, from the light source, the light is coming, so the monochromator is only allowing a specific wavelength of light to pass through, and this solution, so for example this is the incident light. Okay, so the incident light is coming at, just suppose, at 100%. Okay, the 100% of light is coming, and some of it is getting absorbed here. Okay, and the rest is getting transmitted, and that is being detected by the detector. Okay, and then that value is being calculated by your computer. Okay, so this is what the UV spectroscopy is actually is. Okay, so there will be incident light, there will be absorbance, there will be transmitted light, and the detector will detect, and the computer will calculate the value. Okay, so the value for absorption is minus log of IT, that is transmitted light, by the I, that is incident light. Okay, so A is absorbance here, I equal to incident light, and IT is transmitted light, and the L is the path length. Okay, so why path length is important, we'll get it. Okay, so before actually going into the application of the UV spectroscopy, we need to learn few laws, the one of which is Beer-Lambert's law. Okay, so these were two scientists which talk about the absorption of a particular solution with the light, and Beer law actually gave us the simplest of the definition, where he said where the concentration of solution is directly proportional to the absorbance, meaning if the solution concentration is very high, okay, so the absorbance will be very high. Okay, if the concentration of the solution is low, the absorbance will be low. Okay, and the Lambert's law states that the absorption is directly proportional to the path length of the solution. What does the path length mean? So the path that light is traveling. Okay, so this is the path length, so the L is showing here the path length. So from this point to this point is the path length of the uh, light, which is from which the light is traveling in the solution. Okay, so the Beer-Lambert's law combinedly states that the concentration of sample and path length is directly proportional to the absorbance of light. Okay, so A is directly proportional to the concentration of the solution, and A is directly proportional to the path length. Okay, so when we remove this proportionality, we get the E, which is a constant. Okay, so E is the molar absorption coefficient. Okay, so its units is liter per mole centimeter. Okay, and the C is the concentration, which is moles per liter, and L unit has the centimeter. So if you take all the units, okay, and you put it here, so you'll get no unit. Okay, so absorbance has literally no units. Okay, so whenever there's a question saying what is the unit of the absorbance, okay, so it does not have any kind of unit. So the another thing that is required in this UV spectrophotometer is the jump of the electron from the ground state to the higher state. Okay, so the what kind of possibility that can exist? Okay, so we have three ground state. Okay, so one is the bonding state, which is called sigma, another one is the pi, and another one is the non-bonding. Okay, so the sigma and the pi are the bonding states. So pi is where the double bond exists, sigma is where single bond exists, and there is another one called the non-bonding. Okay, there can be a multiple non-bonding scenarios. Okay, so what happens is electron can exist in the sigma, pi, and the non-bonding orbital state. Okay, so when the electron jump from the sigma to the sigma star, okay, as you can see, it is the highest jump among the all. Okay, so it is called the highest jump. Okay, and when the electron jump from the pi to the pi star, okay, or it is called the antibonding. From bonding it is jumping to the antibonding state. Okay, and another scenario that can happen is that is from the non-bonding it can jump to either sigma star or it can jump to the antibonding star. Okay, so this is not that particularly important, but this is the scenario that can actually happen in the UV spectroscopy. Okay, so I know like some of you may not get it and I might not be able to explain it well, but this is the scenario which is actually applicable for the chromophores. Okay, so what happens is this particular application is actually required in the protein biochemistry field. Okay, so let us come to the chromophores before jumping into it. Okay, so what are chromophores? So chromophores are called the chemical group that absorb light at a specific wavelength and imparts color to a molecule. Okay, so for example, so if I have given the light, okay, so if light is given to an electron and it jumps from the sigma to the sigma star, okay, and this jump is actually allowing the electron to go to a higher state, and from this higher state when it'll emit the light. So from the very start slide, so when it'll emit the light, it'll give some color to that particular solution. Okay, so that is why these are called chromophores. Okay, so there are specific chromophores that are present in protein, and these are called tryptophan, tyrosine, and phenylalanine. I know you must have heard the term aromatic amino acids. So these are those. Okay, so the tryptophan, tyrosine, and phenylalanine are the chromophores for the protein molecule. Okay, so what they do is they are usually in the near UV region or the far UV region. Okay, so here the electron jump from the pi to pi star, and in far UV region they jump from pi to pi star and n to pi star. Okay, so you do not have to learn all of these, but you must remember this, that in the near UV region there will be a jump from pi to pi star, and in far UV region there will be a jump from the pi to pi star and n to pi star. Okay, so for example, so tryptophan lambda max is 280. Okay, and tyrosine lambda max is at 275, and phenylalanine lambda max is 258. So lambda max here represent from at which particular wavelength they will show the highest absorption spectra. Okay, so as you can see from the graph, so the tryptophan here showing in the blue has around the maximum spectra around 280 nanometers. Okay, so the tyrosine is also at like around 280, but phenylalanine has the absorption spectra at 260 nanometer, around 260 nanometer. Okay, so what does the E show here? E is the molar absorption coefficient. Okay, so what does it actually represent? Okay, so at this particular concentration, so just suppose if a protein has a higher number of tryptophan, it will show higher number of absorbance. Okay, so E of the tryptophan is 5600, the molar absorption coefficient for the tyrosine is 1400, and for the phenylalanine is 200. You do not have to learn all of these because these will be given in the paper, but just for the reference purpose I have written it here. Okay, so I hope you got the idea of UV spectrophotometer, and this particular slide is not that important, but rest of the thing. So here from the very start, so coming from the UV to the monochromator to the solution to the detector and to the calculation part which is done by computer, it is all important. Okay, another thing that I want to talk about is the what kind of material that is being used here. Okay, so there are mainly two kind of material that are being used. Okay, one is the glass cuvette and another one is a quartz cuvette. Okay, so we generally use glass cuvette for visible spectroscopy and the quartz cuvette for both UV as well as visible, because the spectra range from 340 nanometer to 2000 nanometer, and for the quartz cuvette it ranges from the 190 to 2500 nanometer. But quartz cuvette are usually very costly. Okay, so in most of the labs they generally use the glass cuvette. Okay, So even where I worked, so the quartz cubit cost around like 25,000 for just 2 pieces. So I hope you got the idea like how expensive they must be. So I hope you got the idea of the UV spectrophotometry, and calculation will be very easy. Okay, use for if you want to like actually make the calculation. So if you have given the absorption and if you are given the concentration and the molar absorption coefficient will be given, so you can like measure the length of the particular solution. So you'll be needing only two things. Okay, so you'll be needing the molar absorption coefficient or the either the concentration or the path length. Usually the path length is known to us, okay, because the whatever the quartz that we the quartz cubit or the glass cubit that we use, it has a particular wavelength. Okay, so based on that we can easily calculate our absorption. Okay, so either you have the absorbance, either you have the concentration, or either you have the path length. Okay, so based on this we can calculate the third unit very easily. Okay, so I hope you got the idea, and I thank you for your kind attention. And and in the end we are going to talk about the application of the UV. So the